Alright, so now we're going to have a look at the May-June 2018 paper. It's the Cambridge IGCSE Paper 2, the multiple choice paper for the extended class. Alright, let's start running through that now. Question 1. A length of cotton is measured between 2 points on a ruler. When the length of cotton is wound closely around a pen, it goes round 6 times. What is the distance once around the pen? Okay, let's look at the cotton. Let's see how big it is. There we are. So it starts from 2.4 centimeters and goes all the way up to 15.6 centimeters. There we go. Alright, so the length of the cotton is going to be 15.6 minus 2.4 centimeters. And that is going to give us 13.2 centimeters. And that winds round the pen 6 times. So if I want to find the circumference of the pen once round a pen, then that's going to be 13.2 centimeters divided by 6, which will give me 2.2 centimeters. And that is option A. There we go. Let's look at question number 2. When does an object falling vertically through the air reach terminal velocity? Well, when something's falling, we've got the force due to the weight and the force due to air resistance. When those two are equal, there is no resultant force and no more acceleration, so it's reached terminal velocity. So let's see which sentence reflects that. A, when the acceleration of the object becomes negative. Nope, that's silly. B, when the acceleration of the object is equal to g. Nope, silly. C, when the air resistance equals the weight of the object. There we go, that's looking good. And D, when the air resistance is greater than the weight of the object. No, at that point it would slow down. So there we go. Our answer is C. Let's look at question 3. A car is moving along a straight, level road with constant acceleration. Which graph shows the motion of the car? Constant acceleration. Well, acceleration is changing, well, technically changing velocity over change in time, but I'm going to write change in speed over change in time, because both the graphs we're dealing with down the bottom are speed, and we've got distance up the top, so it's not related to any of the distance graphs. There we go. Neither of those. We're interested in change in speed over change in time. And looking for a constant change of speed over constant change in time, which is option D. C, there's no acceleration because there's no change in speed over any time. Let's look at question number 4. Diagram 1 shows a beam balance. A beaker with a wire loop balances the standard masses. The beaker is then removed and hung from a spring. The spring extends by 5 centimeters as in diagram 2. The experiment is repeated with the same apparatus on the moon, because whilst travelling to the moon you will want to take a beaker with a wire loop, where the acceleration of freefall is less than the Earth. The acceleration of freefall, what's that mean? The value for the gravitational force is smaller. Okay, so let's look at that. Let's look at the first one. What do we know? We know that weight equals mass times gravity, and here we've got two forces acting which both produce a turning effect. They're balanced. So what do we have? We've got force 1 times distance 1 equals force 2 times distance 2, and of course the force on each side comes from the weight. m1 times g times d1 is equal to m2 times g times d2. Now there's no difference in our g on either side. So if I take that and I take it up to the moon, well, the numbers on each side will fall by the same amount. There'll be a smaller value for the gravitational acceleration, which means that if it balances on Earth, it will also balance on the moon. Diagram 2. Well, what do we have? We've got two equations. We've got the force due to a spring that's been extended, F equals kx, and we've got the force due to the weight, weight equals mass times gravity. We've got a situation where they're balanced, kx equals mg. Now, if gravity gets smaller, then what's going to happen to the extension is, in order to balance, that will also get smaller. So it will extend less. Now let's have a look at our 4 options. Which statement describes what happens on the moon? A, the beam balance is balanced and the spring extends by 5 centimeters. No, because the spring will not extend by 5 centimeters. B, the beam is balanced, yep, and the spring extends by less than 5 centimeters, yep, absolutely true. C, the right hand balance is higher, no, it's going to be balanced. Both the balances will be balanced there. There we go. So the answer is B. 5. An object always has mass, but does not always have weight. Well, let's look at that. The weight of an object is given by mass times gravity, and gravity depends on where you are in the universe. Alright, so what must be present and acting on the mass for it to have weight? Well, from this equation we can see, if it's got a mass, it must have gravity acting on it, so we need a gravitational field. You don't need a set of scales, or displace water, or friction due to air resistance. None of those things will affect the weight. 6. A force acting on a moving ball causes its motion to change. The force stays constant. Okay, let's look at this. Force causes something to change. Force is mass times acceleration. The acceleration is a change in motion. What makes the force produce a greater change in the motion of the ball? Well, a greater change would be a greater acceleration. To get a greater acceleration, we would want a smaller mass, because remember, it tells us the force stays constant. So the question is, which one of these options gives us a smaller mass? A, decreasing the total mass of the ball. Well, that pretty much gives us the answer. Let's look at the other ones. Increasing the temperature of the ball will not change the mass. Using a ball with a hollow center but the same mass, so the mass doesn't change. And D, using a different material for the ball so it has a lower density but the same mass. No, so they're using a bigger ball that has less density. A balloon and a mass are attached to a rod that is pivoted at P. The balloon is filled with helium, a gas less dense than air, so that it applies an upward force on the rod. So we get an upward force here and a downward force from the mass. The rod is horizontal and stationary. Okay, so let's have a look at how this is balanced at the moment. We've got a force and a distance acting from a pivot from 2 different things. So the force upward from the balloon multiplied by the distance to the pivot is equal to the force down from the mass multiplied by the distance from the pivot. So what's that going to give me? The force from the balloon multiplied by 0.3 meters is equal to the force from the mass multiplied by 0.2 meters. Okay, I'm going to divide both sides by 0.3. So it's balancing as long as the force from the balloon is 0.2 over 0.3, that's 0.67 times the force from the mass. Alright, so this tells us when it's balanced. Now, let's look at the options we're being given here. Okay, it wants to know what actions will cause the rod to rotate clockwise. A, move the balloon and mass 10 centimeters to the left. Well, let's see what would have to happen for it to be balanced, because balancing makes our lives easier. So for it to be balanced, the force from the balloon would have to be equal to, everything's moving 10 centimeters to the left, so the mass is now at 30 centimeters, 0.3. The balloon is at 40 centimeters, 0.4, times the force from the mass. So that's 0.75 times the force from the mass for it to balance. Let's look at the second option. Move the balloon and the mass 10 centimeters to the right. Okay, let's see what happens there. The force from the balloon is then equal to 0.1, which is where the mass will end up at, divided by 0.2, which is where the balloon will end up at. Alright, out, so that's 0.5 times the force from the mass. Okay, finally move the balloon and mass to the 25 centimeter mark. So the force from the balloon for it to balance. So each one of these ones I'm looking at is for it to balance. Okay, so move them both to the 25 centimeters mark. 0.25 divided by 0.25 Fm, which gives us 1 times the force from the mass. Tis a windy day. So that gives us 1 times the force of the mass. And finally, move the balloon to the 20 centimeter mark and the mass to the 30 centimeter mark. Well, that would give us the force from the balloon. And remember, all of this is to see where it balances. So from this situation, the force from the balloon, well, the mass is now at the 30 centimeter mark, 0.3 meters, divided by where the balloon would be, the 0.2 meters, which is actually 1.5 times the force of the mass. So for it to balance at each of these points, for the first one, there would have to be the balloon would have to produce a force equal to 0.75 times the weight of the force, sorry, from the mass. Okay, so that means we'd need a bigger balloon. So it's not going to produce an upward force, it's going to sink down. The second one, we only need it to produce 0.5 times the force of the mass. We already know it's producing 0.67. There we are, so this would work. B. If we look at C, we need to produce a force equal to 1, or equal to the value of the force from the mass just to balance. And from D, it'd have to be 1.5 times the force from the mass just to balance. There we are, so the only one it can be is B in that case. Now I would have to say that's probably one of the trickiest questions I've seen in a multiple choice in the IGCSE. That's a tricky question to do. And you have to be quite careful when you do these questions. Let's move on to 8. Never spend too long. What I always advise my students to do, always, go through it, do the easy questions first. And then go through it, do the more difficult questions, and then go through it and do the longer questions. That one I've just done there, you could easily lose 10 minutes in an exam on one question for 1 mark. And for what? Do it at the end. Do it at the end when you have a few minutes free, a few minutes available. But always keep your eye on the clock and make sure that when it comes down to it, you've got an answer for everything. Alright, 8. A car is moving in a straight line on a level road. Its engine provides a forward force on the car. A second force of equal size acts on the car due to its resistive forces. So we get a force forward from the engine and a force due to resistance. There we go, and they're equal. What happens? Well, the resultant force in this case is equal to the force from the engine minus the force from the resistance, which is nothing. And of course, that equals ma, which is nothing. So there is no acceleration. No acceleration means the car moves forward at a constant speed. Technically a constant velocity, but you find a lot of times these multiple choice papers play a little bit fast and loose with the variation between velocity and speed. Alright, so it's not A, the car doesn't change direction, you'd need a resultant force for that. It's not C, the car slows down, because you need a resultant force for that. And it's not D, the car speeds up, because you'd need a resultant force for that. It's part B, the car moves at a constant speed. 9. Which expression gives the momentum of an object? Well, momentum, straightforward definition. Momentum is mass times velocity. There we go. 10. As energy is transferred into different forms, it eventually becomes dissipated. That's true. What does this mean? Well, energy never disappears. Never. It changes into one form or to another, and eventually all becomes heat and spreads out across the universe, and the universe will, over a very long time period, undergo a heat death. Now, B, the energy finally changes into every possible form of energy? No. Why would it? C, the energy spreads out among the objects in their surroundings? Yes. And D, the total amount of energy becomes less? No. There we are, so that's answer C. 11. A ball of mass 1.2 kilograms is dropped from a height of 30 meters. As it falls, 25% of its initial gravitational potential energy is transferred to thermal energy, so it's lost 25% of its energy. What is the kinetic energy of the ball just before it hits the ground? Ooh, a tricky question. What do I mean by that? Well, they've told you 25%, but if you've rushed through it, you've probably got fixated on the fact it's 25%. If you lose 25% of the energy, then the ball will keep 75%. And that's what it's asking you about, the energy of the ball. So, what do we have? We want to know about potential energy being converted to the kinetic energy, 75% of it. That's going to be mgh, which is where the kinetic energy will come from. It will come from that potential energy, gravitational potential energy. So, mass times gravity times height multiplied by 0.75. Okay, that's 1.2 kilograms times 10 meters per second squared times 30 meters times 0.75, which will give me a value of 270 joules. There we go. Question 12. A girl hangs by her hands from a bar in the gymnasium. She pulls herself up until her chin is level with the bar. The mass of the girl is 48 kilograms. She pulls herself a distance of 0.25 meters, and she does this in 2 seconds. What is the useful power she uses to pull herself up? Well, let's have a little bit of a look at that. The useful work, let's look at that. The work done is mass times gravity times height. And power is given by work done divided by time. So the power we're interested in, mass times gravity times height divided by time, 48 kilograms times 10 meters per second squared times height of 0.25 meters divided by a time of 2.0 seconds. And that will give me a value of 60 watts. There we go. Question 13. 4 identical beakers are filled with equal volumes of liquid P or Q as shown. Liquid P is more dense than liquid Q. At which point is the pressure the least? Okay, well, pressure in a liquid is density times gravity times height. If I want the smallest pressure, then what I want is the smallest height, so the smallest value of the height, from the surface of the liquid, the smallest depth it's under, and the smallest value for the density. So looking from the surface of the liquid, the only two that are possible are B and D. They're the closest to the surface, so the lowest pressure. And I want the one which is the least density, the smallest density, which is Q, because we know P is more dense than Q, so I want liquid Q up at the top. Option D. 14. An oil tank has a base area of 2.5 meters squared and is filled with oil to a depth of 1.2 meters. The density of the oil is 800 kilograms per meter cubed. What is the force exerted on the base of the tank due to the oil? Ooh. Alright, well, what do we know? We know the force will be due to the weight. So that is given by mass times gravity. Now the mass is given by the volume times density. There we are. So let's put that in. And the volume, of course, is the area times the height. So 2.5 meters squared times height of 1.2 meters times the density of 800 kilograms meters to the minus 3 multiplied by gravity, which is 10 meters per second squared, and that will give me a value 24,000 newtons. There we go. Let's have a look at question 15. When molecules of gas rebound from the wall of a container, the wall experiences a pressure. What is the cause of this pressure? Well, if I've got molecules bouncing around inside a container, what happens is they hit the wall and their momentum changes. We get a change in momentum. And force is just change in momentum divided by change in time. So let's see which one of these corresponds to that. Change in the energy of the molecules? Not necessarily. Change in the momentum of the molecules. There we go, we like that one. Change in the power of the molecules? Nope. Change in the speed of the molecules? No, not that either. Because of course the speed can remain constant. A molecule can bounce off a wall and have a speed of 10 kilometers a second in either direction. But if the velocity changes, you've got a change in velocity of 20 kilometers a second, and that will give you a change in momentum. 16. A student wishes to calibrate a mercury in-glass thermometer with a degrees Celsius scale. Which values should she use for the lower fixed point and for the upper fixed point? Okay, well, it's a degrees Celsius scale, so we're looking at melting ice for the lower fixed point and when water turns to steam for the upper fixed point, pure water and pure ice. Okay, so let's see what corresponds to that. Lower fixed point, melting point of ice, those two are possibilities. Nothing to do with mercury. And upper fixed point, boiling point of water. There we go. It's option B. Question 17. Which statements about boiling and about evaporation are both correct? Boiling, well, boiling takes place throughout the liquid. Think of it when you boil a kettle. So what does that mean? Well, these two are possibilities. And evaporation only occurs at the surface of the liquid. There we are. So it's option C. Right, let's move on. 18. On a cold day, a metal doorknob X and a similar plastic doorknob Y are at the same temperature. Why does X feel cooler to the touch than Y? Well, it's because it's very good at conducting heat away from your hand. Alright, so what are the options? X convects thermal energy better than Y. I'm going to go with no. There. X is a better thermal conductor than Y. Yep, I like that one. X is a better insulator. No, it's a terrible insulator. And X is a better radiator of thermal energy than Y. Well, your hand's in contact, so it's not the radiation that's the issue. B. 19. Light travels at a speed of 2.0 times 10 to the 8 meters per second in a glass block. In the glass, the wavelength of the light is 4.0 times 10 to the negative 7 meters. What is the frequency of the light? Well, let's see. We know that speed equals frequency times wavelength. There we go, put it into a triangle. CF lambda. And we want to find the frequency, so we just cover that over, like so, and that leaves us with speed divided by wavelength. So, frequency equals C over lambda, which gives us 2.0 times 10 to the 8 meters per second divided by 4.0 times 10 to the negative 7 meters, which gives us a frequency of 0.5 times 10 to the 15 hertz, which is 5.0 times 10 to the 14 hertz. There we go, option D. 20. Which arrow on the graph shows the amplitude of the wave? Alright, amplitude is B. If it was wavelength, that would be D. C is 1/2 of the wavelength, and A is just twice the amplitude. So it's B. 21. Scout P signals to Scout Q on the other side of the value by using a mirror to reflect the sun's light. So let's look at that. Sun's light coming in, we need the light to come down this way to reach Scout Q. Which mirror position will allow this to happen? Let's see. Let's examine them. So A, that looks pretty good to me. B, the sunlight's going to bounce back where it came from. C, it's going to go off in the wrong direction entirely, and D is just going to go off towards the ground. So it's option A. 22. A prism is made from transparent plastic. In this plastic, light travels at 0.8 c, where c is the speed of light. In air, light enters one face of the prism at right angles as shown. The light just escapes from the sloping face of the prism. What is the angle theta? Alright, well, first of all, let's find a refractive index n. N is going to be the ratio of the speed of light in a vacuum divided by the speed of light in the medium. So in this case it's going to be 1.0C divided by 0.8C, which is going to give us 1.25. And for our situation here, the light just escapes. We're interested in the angle for total internal reflection. And that angle is given by sine to the negative 1 of 1 over n. So there we go. So the angle that this happens at is sine to the negative 1. And make sure your calculator is in degrees when you do this equation, or this calculation, of 1 divided by n, that's 1 over 1.25, and that will give you a value of 53.2 degrees. So if it just escapes, 53 degrees it is. 23. The sun emits infrared radiation and light. Light from the sun reaches the earth in 8 minutes. Which row gives the correct information about the infrared radiation? Alright, well, infrared radiation is a type of light that we just can't see, so it means it travels at the speed of light. The wavelength of infrared radiation, well, it's longer than visible light, and it should take the same length of time, so we're actually looking at option A. There we go. Because it's not going to take less time, so it certainly isn't B, and it's not D, and the wavelength, if it was shorter, it would have more energy. Infrared light has less energy than visible light. 24. A dolphin has a range of audible frequencies of 150 Hz to 150 kHz. Which range of frequencies can be heard both by humans with good hearing and by dolphins? Well, humans hear from 20 Hz to 20 kHz. So if I look at the crossover between those two, it's going to be from 150 Hz all the way up to 20 kHz. That's where both species can hear. So that gives us a value, or an answer, sorry, of D. 25. A permanent magnet is placed close to a bar of soft iron, so it's going to induce magnetism in the soft iron bar, and it's going to attract it. What are the polarities of end P and end Q? Well, the only reason it attracts it is because this end becomes magnetically south and this end magnetically north, so it pulls it together. Alright, so end P magnetically south, end Q magnetically north. There we go. Option C. 26. A steel magnet is placed inside a coil of wire. Which method is used to demagnetize the magnet? Well, let's have a look at our options. Connect the coil to an AC power supply. Well, that will temporarily demagnetize it 50 times a second before remagnetizing it. So not inordinately useful. B. Connect the coil to an AC power supply and slowly remove the magnet from the coil. This is the way to do it. C. Connect the coil to a DC power supply. Just gives you another magnet. Connect the coil to a DC power supply and slowly remove the magnet if you want that magnet to stay magnety. There we go, let's close that down. 27. The EMF of a rechargeable battery is 6 volts. What does this mean? Well, 1 volt equals 1 joule per coulomb. So which answer corresponds to that? 6 joules is the maximum energy the battery can provide in 1 second. No. 6 joules is the total energy the battery can provide before it has to be recharged. No. C. 6 joules of energy is provided by the battery to drive a 1 coulomb charge around a complete circuit. Yep, that's good. And D. 6 joules is provided by the battery to drive a current of 1 amp around a complete circuit. No. Because 1 amp is 1 coulomb per second. Alright. A student measures the potential difference across the device and the current in the device. Which calculation gives the resistance of the device? So V equals IR. That's the equation we want to use here. V IR. We want the resistance, so we cover that over and we see that resistance equals V over I, voltage over current. And which one corresponds to that? C. There we go. Potential difference divided by current. 29. A water heater is connected to a 230 volt supply and there is a current of 26 amps in the heater. It takes 20 minutes to heat the water to the required temperature. How much energy is supplied by the heater. Alright, let's see about this, because energy equals power times time. And we've got an electrical heater here. So the energy provided by, or the power provided by the heater is current times voltage. So if I want the energy, what I really want is current times voltage times time. And that's going to give me 26 amps times 230 volts times the time. Now I want time in seconds. So times 20 minutes times 60 seconds. And that will give me a value of 7.2 times 10 to the 6 joules. Option D. Which electrical symbol represents a diode? Question 30. Well, that is B. Sometimes you see them like that, sometimes you might see them with a little circle around them. But that's a diode. A is a cell, voltage power supply, really a cell. C is a bulb, and D is a variable resistor. 31. A student sets up this circuit. What is the purpose of the circuit? Well, let's look at what it has. Thermistor. And here, that is a bell. So what are the possibilities? A. To allow a lamp to be made dimmer or brighter as required. There is no lamp. B. To amplify the sound of a voice. No, there is no amplification circuit. C. To light a lamp in the dark. There's still no lamp. And D. To sound a bell when the temperature rises. Sure, I'll go with that. There we are. 32. The diagram shows two voltmeters P and Q connected to a potential divider. Alright, so let's draw out a little circuit and see what happens. We've got 2 voltmeters, and we're going to be asked, that's a sliding connection, what happens to the reading on P and the reading on Q. So let's see what happens. When it's in the middle, we have the voltmeter at P is going to be equal to the voltage at Q. As it gets higher up, the voltmeter at P is going to read less, and the voltmeter at Q is going to read more. And down at the bottom, the voltmeter at P is going to have a very high reading, and the voltmeter at Q is going to have a very low reading. Alright, so what corresponds to that? We're moving towards the top, so we expect a low reading on P and a high reading on Q. So, low reading on P, so it's decreasing, that's possible. Yep, and on Q we want to see increase, we expect it to be answer B. Oh, this looks like a bit of fun. Question number 33. The diagram represents a digital circuit using a NOR gate and an AND gate. Okay, what is the truth table for this circuit? Well, you know what? First thing I'm going to do is I'm going to get rid of 2 of my options. I'm going to put in the top 0, 0, 0, just to see what will happen. If I have 0, 0 going in, an OR gate would give me nothing coming out. So the opposite of nothing coming out would be a 1. A NOR gate will give me a 1. Then I have 1 and a 0 going into an AND gate, and that only gives me a 1 if both of them are 1, so that will give me a 0. So first of all, I expect the top row 0, 0, 0 to have 0 as the output. So it's not C and it's not D. Alright, so now I have to decide between options A and B. And if I look at the bottom, 1, 1, 1 will either give me 1 or it will give me 0. So let's use that as my next input. 1, 1 and 1. So I have 1 and 1 going into my NOR gate. An OR gate would give me a 1 as an output, so the NOR gate is going to give me a 0. And my AND gate is giving me a 0 and a 1. That's only going to give me a 1 as an output if both of the inputs are 1, so they're not. It's going to give me a 0 output. I'm going to say that it's definitely not A then, it's B. And I checked this line, and I checked this line. There we go. 34. Which statement about electromagnetic induction is correct? Okay, electromagnetic induction, what I need is a moving magnetic field relative to a conductor. So I need a conductor to be in a changing magnetic field. Alright. A strong magnet that's held near a stationary conductor. That does nothing. Both of them stationary, there's no changing magnetic field there. The effect occurs when a magnet and conductor both move at the same speed in the same direction. no changing magnetic field for the conductor. The effect occurs when a magnet is moved away from a nearby conductor. Changing magnetic field in a conductor, that will do it. And D, the effect only occurs when a magnet is moved towards a conductor. That will give you electromagnetic induction, but it's not only when it moves towards, it could also be moving away from. So the answer is C. 35. The diagram shows a current carrying conductor in a magnetic field. Which arrow shows the direction of the force acting on the conductor? Well, we use the left-hand rule. First thing we need to know, of course, is the direction of the current. And the current is going to come out of the large end and into the small end. Alright, now we know that, we can use our left-hand rule. We point the first finger in a direction of the field from north to south. Our middle finger on the left hand points in the direction of the current, and our thumb will give us the force, which is option A. There we are. 36. Power losses in transmission cables are reduced by increasing the transmission voltage. What is the explanation for this reduction? Well, okay, let's see what happens. If we get power equals I squared R. That's the equation for power lost. So as we increase the voltage, the current decreases because power equals current times voltage. So as voltage increases, current decreases, power lost also decreases. There we are. So the current decreases, reducing thermal energy losses. Yeah, it heats up the wires less because the wires represent a resistance. B, the current increases, increasing the flow of charge. Nope, rubbish. C, the resistance of the cable increases, decreasing the current. Nope, not true. And D, the resistance of the cable decreases. It would not do that. It'd be nice if things did do that. That's not how the world works, I'm afraid. A is our option. Why would it be nice if it did that? Because suddenly electricity would cost less. 37. In the atomic model, an atom consists of a central mass orbited by smaller particles. Alright, what is the name of the central mass and the orbiting particles? Well, this bit in here is a nucleus. And this bit out here is an electron. The nucleus is made up of neutrons and protons. So the central mass is not called a neutron, it's called the nucleus. The orbiting particle is not an alpha particle, so that leaves us with option D. 38. Nuclear fusion is a reaction that takes place in stars. Which row describes this reaction? Well, nuclear fusion is where you take two small nucleus and jam them together and it releases energy. Alright. So, an atomic nucleus splits into two? Nope, that's not fusion, that's fission. That's also fission. An atomic nuclei join together? Yep. So both those are possible. Energy is released. How do we know it's released? Because the sun's hot. If it was absorbed, then the sun would be cold. There we are. D. 39. The diagram shows emissions from a source passing into the electric field between two charged plates. Alright, whatever it is attracted. We've got two rays travel through. One is not attracted to positive or negative charge. That is a gamma ray. And the one which is attracted to the negative charge is positively charged. So it's an alpha particle, because an alpha particle is two positive charges. If it was attracted to the positive charge, there we go, then that would be a beta particle. But there is no beta particle here. So what is emitted from the source? Well, gamma rays and alpha particles. C. And finally, number 40. The graph shows how the count rate registered by a counter near to a sample of radioactive isotope changes over a period of a few days. The background count rate is 5 counts per minute. Aha! Ooh, that's important. Tricky. What is the half-life of the isotope? Alright, pay attention to this. Why? Because it means we can ignore this entire section above 5, or under 5. This is our count rate for the actual material as it changes. Alright. So what does that mean? Well, it means between 5 and 40, it's registering 40. We're interested in how long it takes before it goes from a count rate of 40 to a count rate of 20. So that'll be when it hits 25. And it hits 25, there we go, after 2 days. Oh, that's a brutal question. So the half-life here is 2 days. And that's a brutal question because the background count rate is 5 counts per minute. A little bit unfair, a little bit harsh, but also a little bit of fun. Exciting question. There we go. Bit of a trick to end off on. So hopefully you've enjoyed me running through that paper. If you have, please feel free to hit the like and subscribe buttons. And you know what? Have a lovely day.